The halogens or halogen elements are a group in the periodic table consisting of 5 chemically related elements: fluorine, chlorine, bromine, iodine, and astatine. The artificially created element 117 may also be a halogen. In the modern IUPAC nomenclature, this group is known as group 17. The group of halogens is the only periodic table group that contains elements in all 3 familiar states of matter at standard temperature and pressure. All of the halogens form acids when bonded to hydrogen. Most halogens are typically produced from minerals or salts. The middle halogens, that is, chlorine, bromine and iodine, are often used as disinfectants. The halogens are also all toxic. History: the fluorine mineral fluorspar was known as early as 1529. Early chemists realized that fluorine compounds contain an undiscovered element, but were unable to isolate it. In 1869, George Gore, an English chemist, ran a current of electricity through hydrofluoric acid and discovered fluorine, but he was unable to prove his results at the time. In 1886, Henri Moissan, a chemist in Paris, performed electrolysis on potassium bifluoride dissolved in waterless hydrofluoric acid, and successfully produced fluorine. Hydrochloric acid was known to alchemists and early chemists. However, elemental chlorine was not produced until 1774, when Carl Wilhelm Scheele heated hydrochloric acid with manganese dioxide. Scheele called the element dephlogisticated muriatic acid, which is how chlorine was known for 33 years. In 1807, Humphrey Davy investigated chlorine and discovered that it is an actual element. Chlorine was used as a poison gas during World War I. Bromine was discovered in the 1820s by Antoine Jar. Copyright Rami Ballard. Ballard discovered bromine by passing chlorine gas through a sample of brine. He originally proposed the name meride for the new element, but the French Academy changed the element's name to bromine. Iodine was discovered by Bernard Courtois, who was using seaweed ash as part of a process for saltpeter manufacture. Courtois typically boiled the seaweed ash with water to generate potassium chloride. However, in 1811, Courtois added sulfuric acid to his process, and found that his process produced purple fumes that condensed into black crystals of iodine. Suspecting that he had discovered a new element, Courtois sent his sample to other chemists for investigation. Iodine was proven to be a new element by Joseph Gay-Lussac. In 1931, Fred Allison claimed to have discovered element 85 with a magneto-optical machine, and named the element alabamine, but was mistaken. In 1937, Jagindra claimed to have discovered element 85 in minerals, and called the element dakine, but he was also mistaken. An attempt at discovering element 85 in 1939 by Horia Hullable and Yvette Cauchois via spectroscopy was also unsuccessful, as was an attempt in the same year by Walter Minder, who discovered an iodine-like element resulting from beta decay of radium. Element 85, now named astatine, was produced successfully in 1940 by Dale R. Corson, K. R. Mackenzie, and Emilio G. Segre, who bombarded bismuth with alpha particles. Etymology: in 1842, the Swedish chemist Baron Jar paragraph N.S. Jacob Berzelius proposed the term halogen a 1/4 II, salt, or sea, and I cubed I micron I 1/2, from I cubed I cubed I 1/2 I 1/4 I plus or minus I to the first, come to be a euro for the 4 elements that produce a sea salt-like substance when they form a compound with a metal. The word halogen had actually first been proposed in 1811 by Johann Salomo Christoph Schweiger as a name for the newly discovered element chlorine, but Davy's proposed term for this element eventually won out, and Schweiger's turn was kept at Berzelius' suggestion as the term for the element group that contains chlorine. Fluorine's name comes from the Latin word fluor, meaning to flow. Chlorine's name comes from the Greek word chloros, meaning greenish-yellow. Bromine's name comes from the Greek word bromos, meaning stench. Iodine's name comes from the Greek word iodes, meaning violet. Astatine's name comes from the Greek word astatos, meaning unstable. Characteristics: chemical. The halogens show trends in chemical bond energy moving from top to bottom of the periodic table column with fluorine deviating slightly. Halogens are highly reactive, and as such can be harmful or lethal to biological organisms in sufficient quantities. This high reactivity is due to the high electronegativity of the atoms due to their high effective nuclear charge. They can gain an electron by reacting with atoms of other elements. Fluorine is one of the most reactive elements in existence, attacking otherwise inert materials such as glass, and forming compounds with the heavier noble gases. It is a corrosive and highly toxic gas. The reactivity of fluorine is such that, if used or stored in laboratory glassware, it can react with glass in the presence of small amounts of water to form silicon tetrafluoride. Thus, fluorine must be handled with substances such as Teflon, extremely dry glass, or metals such as copper or steel, which form a protective layer of fluoride on their surface. The high reactivity of fluorine means that, once it does react with something, it bonds with it so strongly that the resulting molecule is very inert and non-reactive to anything else. For example, Teflon is fluorine bonded with carbon. Molecules, diatomic halogen molecules. The halogens form homonuclear diatomic molecules. As such they form part of the group known as elemental gases. The elements become less reactive and have higher melting points as the atomic number increases. Compounds, hydrogen halides, all of the halogens have been observed to react with hydrogen to form hydrogen halides. For fluorine, chlorine, and bromine, this reaction is in the form of H2 plus X2 or 2HX. However, hydrogen iodide and hydrogen astatine can split back into their constituent elements. The hydrogen-halogen reactions get gradually less reactive toward the heavier halogens. A fluorine-hydrogen reaction is explosive even when it is dark and cold. A chlorine-hydrogen reaction is also explosive, but only in the presence of light and heat. A bromine-hydrogen reaction is even less explosive. It is explosive only when exposed to flames. Iodine and astatine only partially react with hydrogen, forming equilibria. All halogens form binary compounds with hydrogen known as the hydrogen halides, hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, and hydrogen astatine. All of these compounds form acids when mixed with water. Hydrogen fluoride is the only hydrogen halide that forms hydrogen bonds. Hydrochloric acid, hydrobromic acid, hydrolodic acid, and hydroastatic acid are all strong acids, but hydrofluoric acid is a weak acid. All of the hydrogen halides are irritants. Hydrogen fluoride and hydrogen chloride are highly acidic. Hydrogen fluoride is used as an industrial chemical, and is highly toxic, causing pulmonary edema and damaging cells. Hydrogen chloride is also a dangerous chemical. Breathing in gas with more than 50 parts per million of hydrogen chloride can cause death in humans. Hydrogen bromide is even more toxic and irritating than hydrogen chloride. Breathing in gas with more than 30 parts per million of hydrogen bromide can be lethal to humans. Hydrogen iodide, like other hydrogen halides, is toxic. Metal halides. All the halogens are known to react with sodium to form sodium fluoride, sodium chloride, sodium bromide, sodium iodide, and sodium astatine. Heated sodium's reaction with halogens produces bright orange flames. Sodium's reaction with chlorine is in the form of 2Na plus Cl2 or 2NaCl. Iron reacts with fluorine, chlorine, and bromine to form iron, 3, halides. These reactions are in the form of 2Fe plus 3X2 or 2FeX3, however, when iron reacts with iodine, it forms only iron, 2, iodide. Iron wool can react rapidly with fluorine to form the white compound iron, 3, fluoride even in cold temperatures. When chlorine comes into contact with heated iron, they react to form the black iron chloride. However, if the reaction conditions are moist, this reaction will instead result in a reddish-brown product. Iron can also react with bromine to form iron, 3, bromide. This compound is reddish-brown in dry conditions. Iron's reaction with bromine is less reactive than its reaction with fluorine or chlorine. Hot iron can also react with iodine, but it forms iron, 2, iodide. This compound may be gray, but the reaction is always contaminated with excess iodine, so it is not known for sure. Iron's reaction with iodine is less vigorous than its reaction with the lighter halogens. Interhalogen compounds. Interhalogen compounds are in the form of ℏ where X and Y are halogens and N is 1, 3, 5, or 7. Interhalogen compounds contain at most two different halogens. Large interhalogens, such as ClF3, can be produced by a reaction of a pure halogen with a smaller interhalogen such as ClF. All interhalogens except IF7 can be produced by directly combining pure halogens in various conditions. Interhalogens are typically more reactive than all diatomic halogen molecules except F2 because interhalogen bonds are weaker. However, the chemical properties of interhalogens are still roughly the same as those of diatomic halogens. Many interhalogens consist of one or more atoms of fluorine bonding to a heavier halogen. Chlorine can bond with up to 3 fluorine atoms, bromine can bond with up to 5 fluorine atoms, and iodine can bond with up to 7 fluorine atoms. Most interhalogen compounds are covalent gases. However, there are some interhalogens that are liquids, such as BrF3, and many iodine-containing interhalogens are solids. Organohalogen compounds, many synthetic organic compounds such as plastic polymers, and a few natural ones, contain halogen atoms. These are known as halogenated compounds or organic halides. Chlorine is by far the most abundant of the halogens, and the only one needed in relatively large amounts by humans. For example, chloride ions play a key role in brain function by mediating the action of the inhibitory transmitter GABA and are also used by the body to produce stomach acid. Iodine is needed in trace amounts for the production of thyroid hormones such as thyroxine. On the other hand, neither fluorine nor bromine is believed to be essential for humans. Organohalogens are also synthesized through the nucleophilic abstraction reaction. Polyhalogenated compounds. Polyhalogenated compounds are industrially created compounds substituted with multiple halogens. Many of them are very toxic and bioaccumulate in humans, and have a very wide application range. They include the much maligned PCBs, PBDEs, and perfluorinated compounds, as well as numerous other compounds. Reactions. Reactions with water. Fluorine reacts vigorously with water to produce oxygen and hydrogen fluoride, 2F2, G, plus 2 hours 2O, L, O2, G, plus 4HF, AC. Chlorine has maximum solubility of circa 7.1 gCl2 per kg of water at ambient temperature. Dissolved chlorine reacts to form hydrochloric acid and hypochlorous acid, a solution that can be used as a disinfectant or bleach, Cl2, G, plus H2O, L, HCl, AC, plus HClO, AC. Bromine has a solubility of 3.41 g per 100 g of water, but it slowly reacts to form hydrogen bromide and hypobromous acid, Br2, G, plus H2O, L, HBr, AC, plus HBrO, AC. Iodine, however, is minimally soluble in water and does not react with it. However, iodine will form an aqueous solution in the presence of iodide ion, such as by addition of potassium iodide, because the terdide ion is formed. Physical and atomic. The table below is a summary of the key physical and atomic properties of the halogens. Data marked with question marks are either uncertain or are estimations partially based on periodic trends rather than observations. Isotopes. Fluorine has one stable and naturally occurring isotope, fluorine 19. However, there are trace amounts in nature of the radioactive isotope fluorine 23, which occurs via cluster decay of protactinium-231. A total of 18 isotopes of fluorine have been discovered, with atomic masses ranging from 14 to 31. Chlorine has two stable and naturally occurring isotopes, chlorine 35 and chlorine 37. However, there are trace amounts in nature of the isotope chlorine 36, which occurs via spallation of argon 36. A total of 24 isotopes of chlorine have been discovered, with atomic masses ranging from 28 to 51. There are two stable and naturally occurring isotopes of bromine, bromine 79 and bromine 81. A total of 32 isotopes of bromine have been discovered, with atomic masses ranging 67 to 98. There is one stable and naturally occurring isotope of iodine, iodine-127. However, there are trace amounts in nature of the radioactive isotope iodine-129, which occurs via spallation and from the radioactive decay of uranium in ores. Several other radioactive isotopes of iodine have also been created naturally via the decay of uranium. A total of 38 isotopes of iodine have been discovered, with atomic masses ranging from 108 to 145. There are no stable isotopes of astatine. However, there are 3 naturally occurring radioactive isotopes of astatine produced via radioactive decay of uranium, neptunium, and plutonium. These isotopes are astatine-215, astatine-217, and astatine-219. A total of 31 isotopes of astatine have been discovered, with atomic masses ranging from 193 to 223. Production: approximately 6 million metric tons of the fluorine mineral fluorite are produced each year. 400,000 metric tons of hydrofluoric acid are made each year. Fluorine gas is made from hydrofluoric acid produced as a byproduct of phosphoric acid manufacture. Approximately 15,000 metric tons of fluorine gas are made per year. The mineral halite is the mineral that is most commonly mined for chlorine, but the minerals carnallite and sylvite are also mined for chlorine. 40 million metric tons of chlorine are produced each year by the electrolysis of brine. Approximately 450,000 metric tons of bromine are produced each year. 50% of all bromine produced is produced in the United States, 35% in Israel, and most of the remainder in China. Historically, bromine was produced by adding sulfuric acid and bleaching powder to natural brine. However, in modern times, bromine is produced by electrolysis, a method invented by Herbert Dow. It is also possible to produce bromine by passing chlorine through seawater and then passing air through the seawater. In 2003, 22,000 metric tons of iodine were produced. Chile produces 40% of all iodine produced, Japan produces 30%, and smaller amounts are produced in Russia and the United States. Until the 1950s, iodine was extracted from kelp. However, in modern times, iodine is produced in other ways. One way that iodine is produced is by mixing sulfur dioxide with nitrate ores, which contain some iodates. Iodine is also extracted from natural gas fields. Even though astatine is naturally occurring, it is usually produced by bombarding bismuth with alpha particles. Applications: both chlorine and bromine are used as disinfectants for drinking water, swimming pools, fresh wounds, spas, dishes, and surfaces. They kill bacteria and other potentially harmful microorganisms through a process known as sterilization. Their reactivity is also put to use in bleaching. Sodium hypochlorite, which is produced from chlorine, is the active ingredient of most fabric bleaches, and chlorine-derived bleaches are used in the production of some paper products. Chlorine also reacts with sodium to create sodium chloride, which is another name for table salt. In drug discovery, the incorporation of halogen atoms into a lead drug candidate results in analogues that are usually more lipophilic and less water-soluble. As a consequence, halogen atoms are used to improve penetration through lipid membranes and tissues. It follows that there is a tendency for some halogenated drugs to accumulate in adipose tissue. The chemical reactivity of halogen atoms depends on both their point of attachment to the lead and the nature of the halogen. Aromatic halogen groups are far less reactive than aliphatic halogen groups, which can exhibit considerable chemical reactivity. For aliphatic carbon-halogen bonds, the CF bond is the strongest and usually less chemically reactive than aliphatic CH bonds. The other aliphatic halogen bonds are weaker, their reactivity increasing down the periodic table. They are usually more chemically reactive than aliphatic CH bonds. As a consequence, the most common halogen substitutions are the less reactive aromatic fluorine and chlorine groups. Biological role: fluoride anions are found in ivory, bones, teeth, blood, eggs, urine, and hair of organisms. Fluoride anions in very small amounts are essential for humans. There are 0.5 mg per liter of fluorine in human blood. Human bones contain 0.2 to 1.2% fluorine. Human tissue contains approximately 50 parts per billion of fluorine. A typical 70 kg human contains 3 to 6 grams of fluorine. Chloride anions are essential to a large number of species, humans included. The concentration of chlorine in the dry weight of cereals is 10 to 20 parts per million, while in potatoes the concentration of chloride is 0.5%. Plant growth is adversely affected by chloride levels in the soil falling below 2 parts per million. Human blood contains an average of 0.3% chlorine. Human bone typically contains 900 parts per million of chlorine. Human tissue contains approximately 0.2 to 0.5% chlorine. There is a total of 95 grams of chlorine in a typical 70 kg human. Some bromine in the form of the bromide anion is present in all organisms. A biological role for bromine in humans has not been proven, but some organisms contain organobromine compounds. Humans typically consume 1 to 20 mg of bromine per day. There are typically 5 parts per million of bromine in human blood, 7 parts per million of bromine in human bones, and 7 parts per million of bromine in human tissue. A typical 70 kg human contains 260 mg of bromine. Humans typically consume less than 100 micrograms of iodine per day. Iodine deficiency can cause intellectual disability. Organoiodine compounds occur in humans in some of the glands, especially the thyroid gland, as well as the stomach, epidermis, and immune system. Foods containing iodine include cod, oysters, shrimp, herring, lobsters, sunflower seeds, seaweed, and mushrooms. However, iodine is not known to have a biological role in plants. There are typically 0.06 mg per liter of iodine in human blood, 300 parts per billion of iodine in human bones, and 50 to 700 parts per billion of iodine in human tissue. There are 10 to 20 mg of iodine in a typical 70 kg human. Astatine has no biological role. Toxicity: the halogens tend to decrease in toxicity towards the heavier halogens. Fluorine gas is extremely toxic. Breathing fluorine gas at a concentration of 0.1% for several minutes is lethal. Hydrofluoric acid is also toxic, being able to penetrate skin and cause highly painful burns. In addition, fluoride anions are toxic, but not as toxic as pure fluorine. Fluoride can be lethal in amounts of 5 to 10 grams. Prolonged consumption of fluoride above concentrations of 1.5 mg per liter is associated with the risk of dental fluorosis, an aesthetic condition of the teeth. At concentrations above 4 mg per liter, there is an increased risk of developing skeletal fluorosis, a condition in which bone fractures become more common due to the hardening of bones. Current recommended levels in water fluoridation, a way to prevent dental caries, range from 0.7-1.2 mg per liter to avoid the detrimental effects of fluoride while at the same time reaping the benefits. People with levels between normal levels and those required for skeletal fluorosis tend to have symptoms similar to arthritis. Chlorine gas is highly toxic. Breathing in chlorine at a concentration of 3 parts per million can rapidly cause a toxic reaction. Breathing in chlorine at a concentration of 50 parts per million is highly dangerous. Breathing in chlorine at a concentration of 500 parts per million for a few minutes is lethal. Breathing in chlorine gas is highly painful. Hydrochloric acid is a dangerous chemical. Pure bromine is somewhat toxic, but less toxic than fluorine and chlorine. 100 mg of bromine are lethal. Bromide anions are also toxic, but less so than bromine. Bromide has a lethal dose of 30 grams. Iodine is somewhat toxic, being able to irritate the lungs and eyes, with a safety limit of 1 mg per cubic meter. When taken orally, 3 grams of iodine can be lethal. Iodide anions are mostly non-toxic, but these can also be deadly if ingested in large amounts. Astatine is very radioactive and thus highly dangerous. See also, pseudohalogen, halogen bond, halogen lamp, interhalogen, notes. References. Further reading, Greenwood, Norman N. Earnshaw, Alan. Chemistry of the Elements. Butterworth Heinemann. ISBN 0080379419-A.